Just get this out of the way. All right, so thank you for having me. I thought I would just talk a bit about some of the work in my group that we've done with dynamic modeling inference systems. So looking at the transmission dynamics of SARS-CoV-2, what we did beginning at the start of the pandemic, really, and what we've been doing of late as well. Funders, just want to acknowledge them. A whole bunch of collaborators here who've worked on various portions of this. I'd particularly like to note in the left column, Dr. Sen Pei and Dr. Marta Galanti, who've been very instrumental in directing what we're doing. So I actually want to, before going into it in detail, sort of back up and tell you about a field study that we did in New York City that we called the Virome of Manhattan that really informed our thinking when this virus emerged. This study was designed to try to understand, among other things, it had a couple of aims, but one of the big aims was try to understand what's the real prevalence of common respiratory viruses in a typical community such as Manhattan, New York City. How do they get around? What are the rates of asymptomatic infection? And what does that mean for the persistence of these viruses and why they're so ubiquitous? So we had a number of arms to this study, which had field campaigns associated with it. For instance, in one of them, we went into a major tourist attraction in New York City, and we would solicit people who are visiting this tourist attraction. We'd ask them to give us a brief medical history, tell us what their symptoms felt like, really, obviously, over the last 48 hours with respect to 9 common cold symptoms, things like runny nose, sneezing, sore throat, chills, cough. And they would rate that on a Likert scale, none, mild, moderate, or severe. And then we would take a nasopharyngeal swab from them, take it back to the lab and test it for 18 different common respiratory pathogens, all viruses. What we found when we did this study is that these were all adults. They were all going around New York City. They were from all over the world. And in February, for instance, when we did it in the month of February, 9% of them, actually 11% of them, excuse me, 1 in 9 of them was shedding a common respiratory virus. So people were walking around sharing their virus broadly in the community unknowingly all the time. Now, the thing that you're looking at here are data from another arm of this study, which was a cohort that we ran. And in this cohort, we ultimately listed more than 200 individuals who were enrolled. They would give us a medical history at the onset. And then on a daily basis, they would tell us their symptoms vis-a-vis those 9 common cold symptoms. Again, on that same Likert scale. They would just enter this over the phone directly into an electronic database that we had. And we built out from this a time series record of symptomology. In addition, they would also tell us if they had taken medicine because of their respiratory symptoms, if they had stayed home from work or school, or if they had gone to see a clinician, a doctor. And it took all of 30 seconds, and we had a very high compliance rate. And then once a week, regardless of how these individuals felt, we would swab them. We would take a swab, take it back to the lab, and test it for 18 different respiratory viruses. And the results of that, one form of them, are what are shown in this table. What you're seeing in the column that is episodes defines a group of consecutive weekly specimens from a given individual that were positive for the same virus. We allowed 1 week for false negatives or temporary low shedding, but we use that to define episodes because somebody could be shedding the same virus for more than 1 week. Further, we took the 18 viruses and we grouped them by their basic nomenclature. So all the flus are grouped in flu, RSV A and B are all in RSV, et cetera. So you can see the number of episodes that we documented amongst these 200 individuals over a 19-month span that included 2 winter periods. And you see we had 32 instances of influenza infection, 30 documented for RSV, 275 for human rhinovirus, 137 for the endemic coronaviruses. Now, this is all pre-pandemic, so that's things like OC43 and HKU1. The next column shows you the number of those episodes in which the individual sought medical attention. They actually went to see a clinician because of their respiratory symptoms. The column after that shows you the fraction, the probability of seeking medical attention given infection with that virus. And what you can see is those numbers are pretty low. Less than a quarter of the people who had flu went to see a doctor. If you go down the bottom of the column for the coronaviruses, it's 1 in 25 persons went to see a doctor because of the symptoms they experienced during an episode of infection with a coronavirus. You can go further to the right, you can see whether they stayed home, and you can see in all instances it's below 50%, and the probability that they took medicine for it, you can see as well. I'm not showing you asymptomatic versus symptomatic designation because that's actually a very squirrely line. What we could see from the time series that we built up from these 200 plus individuals is that asymptomatic is not an easily definable metric. And as a matter of fact, there really isn't a standard definition in the literature. And that's because different people have different set points. There were people in our cohort who reported respiratory symptoms every single day. Maybe they had chronic rhinitis, maybe they had fibromyalgia, maybe they were just a hypochondriac. We really don't know for certain, but their baseline was non-zero in terms of the reporting of symptoms. There were others that it really didn't matter what they were infected with. They never reported any symptoms. So it's a very relative scale and it's difficult to pin down. But what we really could see is that the true distinction that's important, both in a clinical perspective and from a public health perspective, is documented versus undocumented. Those who seek medical attention versus those who don't. And the reason for this is the way that we monitor respiratory viruses in most communities around the world is passively. We wait for individuals who seek clinical care or want to be tested to come and find us. Those are the individuals who are tested, and they're the only ones who can be captured to tell us how much virus is in circulation, or at least how much is relative to other viruses that might be in circulation. A better detection system would be one that is active, which is what we have right here, but it is at this point very, very expensive to perform this. But from this information, we could see that the vast majority of infections are undocumented. Almost 80% of flu and over 95% of coronavirus infections are undocumented, persons who will never seek medical attention, at least based on these data. So what does that mean? It means to us that the reason these viruses persist, they're so ubiquitous, is because they have a characteristic that allows them to evade detection. What people do when they experience infections with these viruses is what you or I would do when the wintertime if we had a little sniffle or a little cough or sore throat. And that is absolutely nothing. We would still go to work, we'd still go to school, we still go out to restaurants, we still go shopping. If you have a business trip or a vacation, you're still going to get on an airplane. And what are we doing when we do that? Well, we're taking the virus with us and we're sharing it. We're taking it to new communities, both within our locality, and if we get on planes or trains or cars, we're taking it to new locations and sharing it more broadly. So we started to see the emergence of this virus. We got wind of it December 31st, 2019, and we saw the rapid spread of it from its epicenter in Wuhan throughout China. And then we saw that very quickly it was hopping on airplanes and appearing in Thailand and South Korea and Japan and the United States. And when we saw this, we immediately said to ourselves, based on what we had done with this virome project, this pathogen is behaving like a common respiratory pathogen. It's probable that most of the people who have this are not aware that they're infected with it and may never be aware that they're infected with it. So what we decided to do was to build a model inference system to determine whether that was indeed the case and to quantify that. So we do a lot of modeling in my group, and what we did is we built a metapopulation model for the transmission of this new agent, SARS-CoV-2, in China. We represented 375 cities that were linked using Tencent data, which is a location-based service that has penetration in apps like QQ and WeChat, which are very pervasive in Chinese markets, that told us about movement between those 375 cities in the run-up to the Qinyun Spring Festival. We coupled the model further with data assimilation methods. These are Bayesian inference algorithms that allow us to assimilate observations of confirmed cases from the 375 cases into the model system and use it to infer system parameters. Now, we did this in order to simulate a very brief window of time, January 10th through January 23rd. And we focused on this period of time because prior to January 10th, the observations of confirmed cases were rather sparse. And January 23rd was the stop date because that was the date they imposed the lockdown on Wuhan City, which shortly after spread to a majority of China. So it was prior to travel restrictions. That was the aim here. And there's enough of a signal that we could actually observe how is this virus moving through Chinese society at a time when they weren't doing that much to control it, though they did have testing capacity to detect it at that point. Now, within this model, we separately represented documented and undocumented infections. And we wanted to know what the relative numbers of those two quantities were. Furthermore, within the model, we had a separate contagiousness for documented and undocumented infections because we wanted to recognize that it's possible that people who are more clinically manifest with the disease might shed more of the virus, or maybe because they're sequestered away, even less. So we wanted to allow a differential there. Now, for a system like this, before we're actually going to interrogate it with real data, we want to see whether or not it's identifiable. The system is high dimension in terms of its state space because it's got 375 cities, but we only had 6 parameters in them that are shown there on the left. Beta, which is the contact rate, mu, which is the adjustment of that contact rate for persons who are undocumented infections. Theta was an adjustment of the Tencent travel data, knowing that it is going to be an undercount of travel. Z is the latency period. Alpha is the ascertainment rate, which is that delineation of what fraction will be documented. And D is the infectious period. So what we do with this is we run the model, which is stochastic and free simulation. We generate an outbreak with it. Then we take that outbreak and we feed it into the model inference system and see if it can reconstitute estimates of the parameters that span the truth. Here's one example of that. You can see that the distributions of the posterior, which are shown in blue, always span the truth for this instance for all 6 parameters at least. You can also see it for the truth for the reproductive number, which is an aggregate parameter shown in the lower right. We did this over and over again. We broke the system down to 50 cities, to 10 cities. We saw that when we transitioned from 50 to 10, that's when the identifiability of the system started to become corrupted. So we knew that at this scale, at least if we could assume the model is well specified, that it's going to be able to estimate the parameters with some accuracy, some veracity. So we then applied it to actual data, and this shows you the result from it. I want you to focus on the reporting rate, that ascertainment rate alpha. It's 0.14. That indicates that we estimated that only 14% of infections in that 2-week period in China were documented, meaning 86% were undocumented. Furthermore, look at mu. That is the relative transmission rate or the relative contagiousness and transmissibility of those who are undocumented infections. It's 0.55. Indicating our estimate that per person, an undocumented infection is on average about half as contagious as documented infections. The aggregate parameter, the basic reproductive number here, even though it's written RE, is 2.38, which was in line with other estimates at the time for what was going on in China. So one of the next questions is, well, you have these parameter estimates. If you plug them into your model and run free simulations, are you going to recreate what actually happened? This shows you that the X's are observations, the box and whiskers are 100 simulations with the parameters estimates for this metapopulation model. You can see national data, daily cases for Wuhan City, daily cases for Hubei province, in which Wuhan City is, as well as in the lower right, the number of cities with cumulative incidence of more than 10 or more cases. So it's fitting the system well with these parameter estimates. We then actually said, well, we could have the model, let's do a counterfactual simulation. What if we were to say that the undocumented infections can't transmit the virus? Well, that's pretty simple to adjust. We just set that mu parameter to 0 and rerun the model and see what the differential would be. And you can see that here. The red is what you saw on the previous slide with the actual parameter estimates. And now you're seeing the outbreak is simulated with the same number of simulations, but with mu set to 0. In this instance, transmission without transmission from undocumented infections, almost 80% of the confirmed cases disappear. So what does this mean? It means that the lion's share of the transmission of this virus is being supported by undocumented infections. People who don't know they have the infection are sharing it broadly and supporting the rapid dissemination and growth of the outbreak. Furthermore, and I'm not going to show this here, we're able to show that we estimated that pre-symptomatic shedding was taking place among documented infections, and it was taking place for about 2.5 days prior to the onset of symptoms. Now, if we look at the various coronaviruses that we know about that have infected humans, there are 6 other coronaviruses: SARS-1, MERS, the Middle Eastern Respiratory Syndrome, and the 4 seasonal or endemic coronaviruses, which have these funny alphanumeric names you see in parentheses there. Now, SARS-1 had a very high case fatality rate, about 10%. However, it's believed that the subclinical infection rate, undocumented infections, were virtually nil. When they did antibody surveys to try to find out who had been infected in communities that were impacted by it, they were not finding anybody who had these antibodies. So it appears that the vast majority of people who were infected with SARS-1 presented with clinical infection symptoms and were clinically attended. And furthermore, there was no evidence of pre-symptomatic shedding. MERS is a little more wimpy. It's not as transmissible, so it has some difficulties with that, but it too doesn't produce a lot of mild cases amongst those it does infect. It's about only 1 in 5 that are actually mild or asymptomatic. Now, on the other end of the spectrum, you have these seasonal coronaviruses, the ones that produced about 135 infection events in our Virome of Manhattan study. 60% or more are mild or asymptomatic, and very few seek clinical attention. So this viruses get around. They get around because most people who have them don't stop doing their normal business. Well, what we're finding with this one, and we found this out in late January, early February, was that it lay between these two extremes of SARS-1 and the seasonal coronaviruses. It actually was producing a lot of undocumented infections. And like a common respiratory pathogen, this characteristic allowed the virus to spread very rapidly and move geographically as well, because so many people were sharing it unknowingly. At the same time, unlike the seasonal coronaviruses, it has a fat tail, and there are enough people who are experiencing severe symptoms and that result in hospitalization and death, that given the fact that this is a novel respiratory agent to which there is little pre-existing immunity in the population of the world, it's going to spread rapidly through them, and it's going to result in a lot of morbidity and mortality. So once we had done this study, we decided to turn our attentions to the US, where we live. The US had its first case on like January 20th, I believe, might have been January 19th. And it really didn't take off until the end of February, as you can see from this graph. The confirmed cases really shot up and grew exponentially in the early part of March. So what we did is we took that same system and we adapted it for all the counties in the United States. There are 3,142 of them, representing the transmission dynamics in each county, including documented and undocumented infections, and as well considering movement of people between counties, which we could initially get from US Census survey. And then as we went further along and people's travel patterns were disrupted with shutdowns and other things, we started to again use location-based service data to adjust those travel rates between counties. We repeated the process for the early outbreak through March 13th for the US, and we made the same sort of estimate there using just 6 parameters. And in that case, we got a reporting rate of 0.08, so about 1 in 12 rather than 1 in 7 infections was being reported, which was consistent with the very limited testing capacity and the restrictive testing policies that were in place in the US at the time. Now, as a consequence of some of the more severe cases probably being undocumented, the relative transmission rate view is slightly higher than what we saw for China. As things went along, though, we decided that we were going to make the model a little more complex. We're going to begin assimilating deaths, not just cases, but cases and deaths. And we were going to allow certain parameters to vary through time and in space, in particular the contact rate and that ascertainment rate, alpha. Now, this does corrupt the estimation to a certain extent and makes identifiability a little harder of an issue. But we do this because we want to look at the heterogeneity within the country and to make some estimates of what the features are. One of the things we did is an inference and fitting through the spring wave, basically through the beginning of May. Again, we allowed the movement to vary using SafeGraph location-based mobility data, and we focused on a few metropolitan areas in addition to national scales. And we chose those metropolitan areas because they were ones that had experienced substantive numbers of cases in the counties that made up those metropolitan areas. This shows you a fitting that we did for it. You can see how well we were able to fit national cases and deaths, the New York metro area, and the New York for cases and deaths. And then you can see time varying estimates for each of those 6 metropolitan areas for the reproduction number over time. And what you can see is that they started from different positions, and that's not surprising given different densities, car cultures versus subway cultures and public transportation. And they moved afterwards in their descent to lower reproduction numbers, different rates because of different adoptions of non-pharmaceutical interventions. You can also see how the ascertainment rate varied over time in these estimates here. Now, one of the things that we did with these experiments is some counterfactuals. We said, well, look, we have an estimate of how the reproduction number varied through time, and that estimate reflects the implementation of policies and controls aimed at limiting the opportunities for transmission of this virus. Now, some counties acted on this early, others did not at all. Some did it to good effect, others had non-compliant populations. It's highly variable, but it's all reflected in that time series you saw in the last plot of the change in the reproduction number over time, right? So what if we were to take that and say every county did exactly what it did, it had the same policy measures and public compliance with control, except it got its act together 1 week earlier. Rather than having them start as we did on March 15th, we're going to back it up and start it on March 8th. And we also said, what about 2 weeks earlier? Suppose they had done what they'd done, except just 2 weeks earlier, in the very early portion of this exponential growth, just a couple days after the first confirmed death from COVID-19 in the United States. And what you can see in the X's are the observations of cases and deaths at national level, and then cases and deaths for the New York metro area. And then you can see the counterfactual simulations if we move controls earlier, 1 week earlier or 2 weeks earlier. And again, this is on a county by county basis. If a county didn't do anything, nothing is done 1 week earlier or 2 weeks earlier. So what you can see is that if it was 1 week earlier, it results in roughly a 50% reduction in cases and deaths, even more so for the New York metropolitan area. And if it was 2 weeks earlier, it's an even greater effect. This may be somewhat obvious at this point, but if you act on an exponentiating process early on, you're going to make better control of it. The point in making this at the time, though, was going forward when we did this in May to say that we have to be very, very vigilant. That if we start to see rebounding, and at this time in the United States, there were lots of governors who were reopening restaurants and stores and whatnot, that if we're not careful, that it could rebound and explode in our face. And if we delay response, it would get even worse. Unfortunately, that is what happened in the US. There was a major outbreak during the summertime in the Sun Belt, particularly on the heels of some of the major holidays in the United States, Memorial Day and July 4th. And there was limited response in a timely fashion and a lot of problems. Now, more recently, we've taken this system again, which has been further adapted, and we've applied it to the whole of 2020 to look at what are the differences in characteristics over time and response. And one of the things we're additionally able to do at this point, because there are seroprevalence surveys, is to compare our fitting of the model and the number of people that we think are infected from our inference from cases or cases and deaths with the number that have been captured by those seroprevalence surveys as having been infected. And what you can see in the upper right is that cross-validation that we're able to do with the model. The colors just indicate different dates, and each one of those dots is a different area. There are 10 cities or locations. Some of them are states, some of them are cities, some of them are counties in which they conducted these seroprevalence surveys at different time points. You can see the fitting again of daily cases nationally and for the New York metropolitan area in the upper left. And you can see that ascertainment rate that we talked about so much and how it rose over time. As testing capacity increased, we saw increasing numbers or increasing fractions of cases being documented, though the rate at which it climbed and the level to which it climbed differed. You can see a place like Phoenix gets to the highest level of any of the places in the country, whereas Chicago seems to continually be more muted. One of the other things that we're able to get from this was what's the susceptibility of the population, because we're not just looking at confirmed cases, but total infections, both the documented and undocumented. And you can see what our estimates for the end of the year were. And they roughly said that it looked like about 68, 69% of the population remain susceptible at the end of 2020. At this point, we're pushing 70 is what our latest estimates are. Excuse me, we're pushing 60%. We're moving it down. Excuse me, I'm going the wrong way. Of the population remains susceptible. So at this point, we're seeing over a third of the country has been infected with this virus. There is some variability as you go from place to place. As you can see, Miami seems to have had much more penetration in its community. And if you look at the map on the lower right, that shows you susceptibility on a county by county basis for December 1st. You can see in the area of the upper Midwest of the Dakotas, Minnesota, Wisconsin, that area, that it's getting very white, and that means very low susceptibility, which means a large portions of the populations have been infected. And indeed, in some of the counties in places like the Dakotas, there are counties where 1 in 6 persons has been a confirmed case. So you're looking at very high penetrance of this virus. The last thing I want to talk about is some work we've been doing recently on vaccination, on what needs to be done with the vaccine rollout, at least in the United States, though it certainly has implications elsewhere. And what we looked at is that we have these vaccines that have been approved in the United States. And at this point, there are 2 in the US that are approved, the Pfizer BioNTech and the Moderna. And both of them are the mRNA technology. They have high efficacy. The initial rollout beginning December 14th with the Pfizer vaccine, and then a week later, the Moderna started also, was slower than expected, but the hope was to get to 5 million doses per week. And that's what we modeled in this one simulation I'm going to show you. And what we did is we varied the non-pharmaceutical interventions that were in place. We started basically on January 4th, and we said 3 weeks in, we're going to have 5 million doses delivered to new people each week. And we're going to try different non-pharmaceutical interventions. The baseline scenario actually is no vaccination, and the MPI is being completely relaxed immediately, and assuming in this instance a reproduction number, basic reproduction number of 2.8. And we did this for different ones here, but I'm just showing one. What you see is that SO scenario is the attack rate and the death rate in this scenario with no vaccination and all NPIs given up on, the attack rate from January 4th onward, not the total attack rate, but just from January 4th onward. What you're seeing in S1 through S5 are different scenarios, all of which have the vaccine, but they have different levels of MPI control. In S1, the MPIs again are relaxed immediately, but the vaccine is rolled out. And what you can see is that the reduction in deaths and cases or infections is not that great. It's only a small reduction. And then if you want to see appreciable reductions in death averted and cases averted, it really should be infections averted there, then you need to either strengthen the MPIs or keep them in current and only gradually relax them. As a matter of fact, the S4 scheme in which you increase the MPIs, not surprisingly, prevents people from picking up the virus as much while the vaccine's rolling out. So essentially we have a race between virus and vaccine. And the aim is to vaccinate as many people as possible prior to their infection in order to protect them. And in order to do that effectively, we have to hold on to non-pharmaceutical interventions for the foreseeable future. It may, in some instances, seem like a fairly obvious public health message, but we felt it was one that really needs to get out there. As a matter of fact, the New York Times picked up this, and they ran a story with their own graphics, and their graphics are a heck of a lot better than ours. So this is what it looks like. This shows you if current restrictions remain in place until late January with the vaccine rollout, and then if the restrictions were lifted on February 1st, and you can see 29 million additional total infections being estimated in this scenario. This just shows you a range of scenarios. With strengthening until late July, you'd have 19 million fewer than if you just held them in place. If you strengthened at least until February, we did this in January, 9 million fewer. And then if you lifted earlier, you're getting more infections. So they had all sorts of nice graphics about it, but that is the message. So I will stop here, and I'd be very happy to take any questions you might have.
Right. Thank you, Jeffrey, for a very, very nice talk. So now, as usual, if you have questions, just raise your hand, and I will allow you to talk. So in the meantime, I was wondering if you had a possibility in your model to make this probability of the development of being reported. Can you make it change over time?
That's what that ascertainment rate does. So that ascertainment rate I talked to, that's it changing over time. So Here, let me just go back and show you the plot here.
Yeah, yeah.
So right here, this is the ascertainment rate shown over time.
Mm-hmm.
The box and whiskers here represent different counties at the national scale. Here, this is different counties within New York metro area, but it's showing you each month. So this is March through December right here. And you're just seeing the average. We just did it at a monthly clip. We averaged the estimates over that time period. And so what you're seeing is that it rises over time. As a matter of fact, if you aggregate and do a weighted average over the whole of the year, it's about 21% of infections were confirmed. But you can see that by the end of the year, it was up to about 24%. And early in the year, it was well below 20%.
Oh, okay. Okay, so it aggregates in a way a lot of factors, but probably public awareness and
Yes.
so
Yeah. So really, it's an integration. So we're estimating it from cases and deaths. In this case, just cases, because we wanted to be independent of it to make good estimates of the infection fatality rate and the case fatality rate. And we didn't want to feed that in, but the estimate here is something that's done at a county basis in order to try to get a sense of how that ascertainment rate is changing over time. And the ascertainment rate is going to reflect all those interventions and desires that are out there. Essentially, what is the availability of testing? What is the demand on it? And it's an inference that we're making. We don't have specifics that we're feeding in that say, this is what was observed in terms of the number of people who came in to be tested.
right. Thank you. So that was actually one of the things that I was wondering. Maybe I skipped it during your talk. Is how do you do to actually estimate this ascertainment rate? Do you use additional data on top of cumulative number of cases in particular?
No, it actually just used in the initial thing that we did in China, for instance, when we estimated the ascertainment rate for that period, it was just the case data
Yeah.
and it was just the mobility between. Those were the two data inputs. And the whole point for going through what we call that synthetic test, where we're establishing the identifiability of the system, was to convince ourselves as well as the reviewers that the system was robust. I mean, a critical feature of this type of thing is, are you going to get trapped in a local minima? Are you not going to be able to find the globally appropriate solution that provides you the best estimates of what those parameters should be? And what we were able to show from the synthetic tests is that we're able, with that suite of data, when we bring a lot of case data in from multiple different counties into a metapopulation structure, we're able to achieve identifiability, where we're able to capture the truth within our 95% credible intervals.
Right. Well, thank you for this precision.
Mm-hmm.
Any other question?
I think Silvio.
Oh, right.
Yes. Yeah. Thanks for the very informative talk. So I really do have a question about the synthetic test part. So you were saying that initially you were trying to increase the number of patches that you have, and so that you will have more data points at the time. So that guarantees you to be able to estimate like 6 different parameters over there. So I'm just wondering if you have extremely more case data. For example, if you're considering like more than 100 patches data. So if you have too many data, so what would happen then?
You know, that didn't appear to be a problem. So actually we had that in the first model. It was 375 cities. And what we found is that we tested 375, we tested 100, we tested 50, 25, 10, 2, 1. And when we got down to 10, the identifiability of the system deteriorated. We were no longer able to identify the truth. Now, when you do one of those synthetic tests, you have a hard assumption, which is that your model's not misspecified for reality. So just remember that if our model is a poor reflection of what's actually going on with the transmission dynamics, error is going to come in another fashion. But putting that aside, it seemed to be that the more cities, the better the estimate would be. Now, in that truth, we're doing that test assuming that there is one ascertainment rate, one contact rate in all the cities. Now that in and of itself means that we're imposing an average on that solution. In actuality, I think what you're getting at is, you know, where I sit in Manhattan, New York, this is a very dense population, right? And in normal times, I run into hundreds, if not thousands of people a day. I go out, I get on the subway, I go to work, I go to stores. I'm constantly running into people. And that's very different from a remote area in the United States where it's a car culture and ranches and there's just not a lot of people, sparse population. So to have them have the same parameters, the same contact rate, and particularly as testing changes, to have them have the same ascertainment rate, that doesn't make sense. So if I bring in a lot of localities and I give each one of them its own, at least beta and alpha in this model, contact rate and ascertainment rate, which is what we've done, we know there is some erosion in our ability to identify the system accurately. However, there's a lot more cases now to work from, and that's also why we do that cross validation using that independent estimate of cumulative infections that we get from seroprevalence data. So if our estimates of total infections over time can map onto the seroprevalence estimates of the number of people who've been infected, then we're at least checking the model that way.
Oh, I see. So that's kind of another, like, once you have more seroprevalence data, you can try to validate whatever.
Exactly. It's wholly external to the system, and we can use that as an additional validation, which is what we've done.
I see. Thank you so much. Thanks.
Yep.
I think Jean Wong have a question also.
Oh, Jeffrey, it's a normal question now when you talk about the race between vaccination and disease. Would that variation to a variant of concerns would be a real concern as well? Or?
Oh, of course, it's a huge issue. So, look, if you wanted to look at this and pretend that the virus that we're looking at is going to be like measles, where you get a vaccine and it's going to confer immunity lifelong, then it's a very simple issue, and it's just a straight race between the virus and the vaccine. But that doesn't appear to be the case, and I didn't think it was going to be the case to begin with. We've had real concerns about reinfection, and the question was, based on the fact that we see so much reinfection in the endemic coronaviruses. People get them over and over and over again, in spite of everybody having antibodies. Virtually 90% of the people have antibodies against all 4 seasonal coronaviruses, yet we get them over and over again. It appears now, I'm getting more and more to understand that this is really probably not waning immunity. It's immune escape. When this virus came out, the initial observations of its mutation rate were that it was about as 10th as fast at picking up point mutations as influenza, which was sort of this encouraging idea that, well, maybe this is going to be a slow process if it happens at all. That maybe people will be prone to reinfection, but maybe it'll be on the timescale of 10 years, that initial infection will confer a relatively long-lasting immunity, as would vaccination. What we've seen instead with these new variants of concern is there are also deletion events as well. And there's also some real selective pressure going on. There's some recent articles that came out, one of an immunocompromised patient who had, infection for over 100 days, and each new medicine treatment added a different selective pressure and was selecting within host for new variants in that person. So these viruses really can drift and they really can move. We already see, South Africa is not going to use the AstraZeneca vaccine because it is not sufficiently cross-reactive, according to their own experiments, with the South African variant of concern. And this kind of immune escape is probably going to lead us in the quandary that we're currently in with flu. And what it poses is the question of, well, how frequently is it going to happen? Whether or not vaccine manufacturers can crank out new vaccines, test for their safety and immunogenicity, and get them into individuals to protect to what is currently in circulation with some accuracy. Can they predict what will be happening 6 months down the pike? Because it will take some time. And whether booster shots with different variants are going to confer the kind of adaptive immune response that's going to be targeted enough, or will your prior immunity, your prior adaptive immune response, either to earlier vaccinations or infections over your whole lifespan, are they going to corrupt it? In other words, is the efficacy of the vaccine is going to be eroded? Those are all outstanding questions, as well as the big one, which is, are people going to, because of some partial immunity from existing T cells or memory B cell antibodies, have milder infections or milder outcomes generally upon reinfection. If that is the case, which is really what happened after 1918 and 1968, those pandemics settled into being the seasonal flus, and you don't see the excursions of mortality after the initial pandemic phase for either of those viruses. That we're able to handle them better, that they're not disrupting our hospital systems and overwhelming them, and that people are generally going to have milder outcomes. That would be a good scenario. A nightmare scenario would be that it's just as severe or even worse as some new variants come out, that we can't control them and they're landing even more people in the hospital because of some antibody-dependent enhancement or some other mechanism that comes into play. So there's a lot out there that we don't know that we have to figure out along the way. And it's not to, put horror scenarios out there, but these are realistic. We've seen them with other viruses, just not with something as pervasive as this. Hopefully it will do what maybe 1918 did and settle down into something milder and more approachable and manageable.
Jeffrey, another question related to because your team has studied both the Wuhan cases and in comparison with the states, especially New York. So my understanding, your estimation of the reproduction number in Wuhan is 2.8.
2.4. It was 2.4.
2.4. Yeah. So so Wuhan really, the cases really started right before Chinese New Year. And you mentioned that really it's the contact plays a role, and its early stage, people did not realize the transmissibility at that time. So how could it be that base reproduction number is so comparable with what is reported, for example, in my city, Toronto, is 2.5. So I just cannot understand just how wide the scale is so close. I mean, in such dense city with lots of activities.
I don't have an answer for that. The estimates of the basic reproduction number, and let's be careful that we're talking about the basic reproduction number and not a time-varying reproduction number as observed that is being suppressed by non-pharmaceutical interventions. That number is going to vary from place to place, right? It's going to vary for those same reasons I talked about, how in Manhattan, which is a densely populated area, compared to a very rural place in the middle of nowhere in Manitoba, that's not going to have nearly the number of people around, not nearly the person-to-person contact, and not nearly the opportunities for transmission. So you're going to see some real differences there. Variably, we've seen estimates of the reproduction number, the basic reproduction number, that have been very high in some instances and all the way down to 2, roughly, and even below that, maybe in a few instances. Most of the estimates early on were in the 2 to 3 range, and that happens to be what we've estimated for it. I think in April and May, you started to see additional teams coming out with estimates that saying, no, it's more like 4 or 5. I have never systematically gone through it to try to really figure out, are they talking about the effective reproductive number, the basic reproductive number, the time-varying reproductive number, what setting are they looking at, et cetera. And I think a systematic review of that may exist out there, but I haven't looked at it closely. To me, the critical parameter of estimate is the effective reproduction number. Once you factor in time-varying controls, seasonality, as well as the susceptibility of the population, that's the thing that really dictates whether or not an outbreak takes off. Different models can play around with both of those. If they're not identifiable, they can trade those off against each other. In other words, they can inflate the basic reproduction number or time-varying reproduction number and reduce or increase the susceptibility of the population. Alternately, did I get that right? They can increase the reproduction number and reduce the susceptibility, or they can reduce the reproduction number and increase the susceptibility and get to roughly the same position with the effective reproduction number explaining case growth or case diminution. You can do that. If you're going to do it statistically, you got to make some assumptions on either the infectious period or the serial interval or the generation time in your model. And in doing so, and you have to impose some sort of susceptibility. If it's early on, you assume it's 100%, right? If you're going to do it with a mathematical model, you're going to estimate all of them simultaneously, perhaps. But you have this give and take that you have there that brings again to this issue of identifiability. I think somebody should do a good review of this and should flag methods that are being incorporated and whether there are issues of identifiability and whether they've actually been interrogated before putting a result out so that we know the validity or at least the confidence with which we should view each result. Then we got to compare across control measures, population density, and other factors, because undoubtedly there are going to be some differences.
Thank you, Jeff.
Okay, so maybe if there is no other question, it's time to close the session. So thank you all for participating. Thank you, Jeffrey and Jean, for two very nice talks. And we'll see you in about 2 weeks with two more sessions. Well, that's it.
Thank you very much. Bye-bye.
Thank you.
Take care.
Bye.
Bye-bye.
Bye-bye.
Thank you. Merci beaucoup.